Chapter 5 talks about the greenhouse effect. And before we go into the greenhouse effect, we need to understand what makes a gas a greenhouse gas. To complete this model, please complete the pre-lecture assignment. Go through the learning module, explain climate change, this link right here. There's a quiz here too, so complete that. Read the associated pages in the textbook. Once again, this is chapter 5. You're going to be watching this video, and at the end of everything, complete quiz 4 to check understanding. And there is an assignment 7, that is due on Sunday at 11:45. Our favorite molecule right now is ozone. We know that ozone has a Lewis structure. It is a resonance stabilized structure, sort of like this. What happens when UV light strikes this? UV light is a highly energetic radiation, so the energy is enough to break the bonds and give you an O2 and an O. IR radiation has a higher wavelength, so if you look at E is equal to hc by lambda, if there's a higher wavelength, then it has lower energy. So IR radiation or infrared is a less energetic radiation. It goes from 700 nanometers to 1 millimeter, so longer wavelengths. And what can IR radiation do to ozone? So we have a molecule of ozone. Now the IR radiation is coming through. What is the effect of this on the ozone? It cannot break bonds. This cannot happen. So no breaking bonds. On the other hand, what can happen is you can have what is known as vibrational motion. That is basically that the bonds are usually a certain length, and when the IR radiation strikes, they can lengthen equally on both sides, which is the symmetric stretching. Or they could lengthen one side a little bit longer, one side a little bit shorter. This is your asymmetric stretching. So instead of bonds actually breaking, they just increase or decrease in length. And the third vibrational motion that can happen is bending. So you know that there's an angle between these oxygens, and there can be some sashaying and bending or changing of these angles. So just to summarize, you have a molecule, and when a molecule is subjected to IR radiation, three things can happen. One is symmetric stretching, second asymmetric stretching, and third is bending. Also remember that light is quantized. So light is most likely to be absorbed by a molecule when its frequency exactly matches the frequency of an internal motion. So there's a certain frequency that matches the symmetric stretch. There's a certain frequency that matches this asymmetric stretch. There's a certain frequency that corresponds to this bending. And unless the light of the correct frequency hits this molecule, symmetric stretch will not take place. Unless the frequency of the light exactly corresponds to the asymmetric stretch of a particular molecule, asymmetric stretch is not going to take place. So I just said light is most likely to be absorbed by a molecule when its frequency almost exactly matches the frequency of an internal motion within the molecule. This statement is on page 175. So when is it most likely to be absorbed? For the IR region, you are looking for the selection rule, a change in dipole moment. The absorption of light by a molecule occurs most efficiently when the frequencies of light of one of the molecules and the vibrations almost exactly match. Sometimes the vibrations might not exactly match, they might be a little bit higher, and in that case, some stretching will take place, and a lesser energy rotation will take place. So IR radiation has the power to do both vibrations and rotation. For UV, you can break bonds, you can vibrate, you can rotate. For IR, you can only vibrate and rotate, not break bonds. And if you take an even longer wavelength radiation, this is microwave, the only thing that microwaves can do is rotate molecules. They can't bond stretch or do anything like that. They simply jiggle the molecules around, which is how your food gets hot in the microwave. So, to recap, an IR vibration can essentially cause two things: vibrational essentially, but if you are giving it a little bit extra energy, not exactly corresponding to the symmetric stretch, then a certain amount of rotation will also take place. But we're really interested in this vibration. About 10 to the power 13 vibrations take place every second. So these molecules on a regular basis are stretching and bending 10 to the power 13 times each second. That's huge. And I also want you to understand that within the IR region, you have what is known as thermal IR, which is what we're most interested when it comes to greenhouse gases, because when we think thermal IR, we're thinking heat, and that is specifically between 5 and 100 micrometers. This is important range to know. If a molecule has to absorb IR, or even specifically thermal IR, then we have to look at what is known as a selection rule. When will a molecule absorb IR? I told you there are certain frequencies that has to match. How do we determine that those certain frequencies are matched? Selection rule is as follows. Dipole moment change needs to take place during a vibration. A vibration being a symmetric stretch, an asymmetric stretch, or a bending. So let's look at ozone. You have to first draw the Lewis structure of the molecule and determine if this molecule is polar. If you looked at the pre-assignment, it teaches you how to find out if a molecule is polar. In this case, it looks like the electronegativity of oxygen are not greater than 0.6. However, this bond is a double bond, this bond is a single bond. So the dipole moment is not equal to 0. So this is a polar molecule. Any molecule that does not have a 0 dipole moment is definitely IR active. So if a molecule does not have a non-zero dipole moment, then automatically that molecule is IR active. So first thing to understand is that if a molecule already has a dipole moment, then yes, it is IR active. Carbon dioxide is sort of special because when you draw the Lewis structure of carbon dioxide, this is what I come up with. And we find that the dipole of carbon 2.5, the electronegativity of oxygen 3.5. So my arrow points towards the oxygen, my polarity arrow points always towards the one that has the higher electronegativity. And we find that we have two arrows in opposite directions. So think about a tug of war where two things are pulling in equal and opposite directions. So equal and opposite force. So what happens here is that they cancel each other out, which means the dipole moment is 0 for carbon dioxide. So remember I told you if the dipole moment is not zero, then IR active. What happens if the dipole moment is zero? If the dipole moment is zero, we need to go one step further. Understand that the selection rule is not that it has to have a dipole, but during a symmetric, asymmetric, or bending vibration, the dipole has to change. So, we have carbon dioxide that is simply like this, and that particular molecule has a dipole moment equal to zero. A symmetric stretch is where both of these bonds sort of elongate equally on both sides. We still have an equal and opposite force pulling on both sides. Therefore, the dipoles cancel out and the dipole is still zero. No change in dipole moment. Therefore, by definition, the selection rule for IR is that you have to have a change in dipole moment. So, the symmetric stretch for carbon dioxide is not IR active because the dipole did not change. Asymmetric stretch is where one side elongates a little less, the other side elongates a little bit more. So this is how I would show asymmetric stretching. One side a little bit more, the other side a little bit less. See what happens here. The pulls are still this way and this way, but this arrow is much longer than this arrow. So no longer is the pull equal and opposite. It's still opposite, but not equal. This means now the dipole is not zero, which means there is a change in dipole moment. If there is a change in dipole moment during a stretching, bending, or stretching or bending event, then this mode is IR active. So carbon dioxide, the asymmetric stretch is IR active. Therefore, carbon dioxide is an IR active molecule. It is what we call a greenhouse gas. An IR active molecule is a greenhouse gas. Finally, let's look at bending. We still have the same carbon dioxide, double bonds on both sides. Make sure to show your lone pairs. And bending means that this bond slightly from being linear sort of becomes nonlinear. So no longer again is it equal and opposite. Here the dipole was zero. But when you bend that bond a little bit, it's no longer able to cancel each other out. Now your dipole is not equal to zero. We have a change in dipole moment, and therefore we call this molecule or this vibration IR active. So to summarize, carbon dioxide dipole moment equals zero, non-polar molecule. But even though it is polar, when I stretch symmetrically, I still have a zero dipole moment. So not IR active because there's no change from the status quo. When I do asymmetric, on the other hand, I get a non-zero dipole moment, a change in dipole moment. Therefore, this mode is IR active. When I look at bending, once again I get a non-zero dipole moment. Therefore, this is also IR active. Even if one of these vibrations are IR active, and in this case it's two of them, we call that molecule a greenhouse gas. We saw carbon dioxide, we saw to a certain extent ozone. So if a molecule already has a dipole moment, then it is going to be IR active, but does not mean that if it doesn't have a dipole moment, it's not going to be IR active. What we're looking for is a change in dipole moment during a vibrational activity. What happens in case of a diatomic molecule like nitrogen, which is what most of the atmosphere is made up of? Again, you see there is no net dipole moment. There is no bending possible in these types of molecules. There is no asymmetric stretch. There's only a symmetric stretch possible, and there is no change in dipole moment. So things like N2, H2, O2, and noble gases like argon, xenon, etc., these are automatically not IR active. In the assignment, I've basically given you N2O and CO as an example. So CO is C triple bond O. Remember, draw the Lewis structure. Show me the symmetric, asymmetric, and bending. There will not be any bending here in a diatomic molecule. No bending in a diatomic molecule. Whereas N2O, you'll have asymmetric, symmetric, and bending. And you'll have to determine which one is IR active, which one is not. Remember, you are looking for a change in dipole moment. Next lecture, we will learn how a greenhouse gas, an IR active molecule is a greenhouse gas, and how those molecules then contribute to climate change. So remember, this is what the infrared absorption spectrum for carbon dioxide looks like. You see two ranges of maximum absorption. One of them corresponds to the asymmetric stretch, the other corresponds to the bending stretch. But I want you to also remember the thermal IR concept. So where does the thermal IR lie? So thermal IR is only between 5 and 100. This is the IR that specifically corresponds to heat, not a general IR, but specifically to heat, hotness. And you see that the first band is in the 4 region, so this is not thermal IR. So the only one of the bands in carbon dioxide is thermal IR. Two last things. If you wanted to see molecules vibrate and bend and things like that, this is a great YouTube video that will show you, so you can watch. And I also wanted to talk about why these ranges rather than sharp peaks. Again, you would expect sharp peaks because light is quantized, but the broader peaks correspond to not only vibration that is possible due to IR radiation, but also rotation. So because two things are happening, and because the energies are a little bit spread out for two things, you have slightly broader bands. Remember, IR principally does vibration, but can also do rotation. Please feel free to use the discussion board to post any questions, and remember, due dates are Sunday next week.